All right, so welcome to lesson 29 in the series. I'm going calligraphy pen for you friends at home. Welcome to lesson 29. This is where we make a giant jump. We've been talking about series and whether series converge and under what circumstances series converge. And now we wish to take a look at series of a much different and yet oddly similar type. Today we take a look at what are called power series, and you're going to see some instant familiarity and also take a deep breath in horror. Let's talk about what we mean by a power series about x equals a. This is the first time we've seen the letter X in a long, long time. All of our series have had N's in them, and these series will have N's in them, but this is the first time X plays in. A power series about X equals A is a series of the form. It's a sum as N goes from 0 to infinity of some constant, call it c sub n, very good, times x minus a to the n. So basically, what is this? Well, you have a number, and then you have a number times x minus a, and then you have another number times x minus a squared, and it just keeps going. That's what this is. A power series looks an awful lot like a polynomial that just doesn't stop. It goes on and on and on. Yeah, it goes on and on and on. To say that it's about x equals a indicates that all of the powers are x minus a to a power. That's going to play a role as we go on this week. The number A is called the center of the power series. And in this course, the c sub i's are real coefficients. No 3 minus 2 i's in the bunch. So you may be wondering with me, why would I ever wish to study series of this type? Well, if you take polynomials in sequence, sometimes they do pretty cool things. And that is where we're heading. We're heading to a place where these infinite polynomials, I mean, they're polynomials, but they go on and on forever. So these infinite polynomials converge to some functions that you might not think of as polynomials because they're not polynomials unless you go dot, dot, dot. So consider the following. Bill Nye the Science Guy. So the series 1 plus x squared plus x cubed plus dot, 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 where the nth term is x to the n, and so on. Just a little bit about notation while we're here. We list a couple of specific terms, and then a plus dot, dot, dot to indicate the pattern continues, and then a plus the general term, and then a plus dot, dot, dot. It's all necessary. You wouldn't put a general term in without some pluses on either side. And you have to have the dot, dot, dot to indicate that it goes on forever. And you have to have the dot, dot, dot to indicate that this is a pattern. Okay, so when you write things out, a few specific terms, the pattern continues, plus a general term plus, and the ellipsis to indicate that it goes on and on forever. I would like to know on what interval does this converge? And the first thought that comes to my mind is this thought. Isn't this a thought that comes to your mind? Isn't that one of those things you're thinking about? What do we know about geometric series? Geometric series converge when the absolute value of the common ratio is less than 1. Well, what does that mean in this case? What is the common ratio? Right. So this converges when -1 is less than x is less than 1. This will diverge when x is 1, 1 plus 1 plus 1 plus 1, and so on. It'll diverge when x is -1. And you should convince yourself that it will diverge when x is -1. And then obviously for x is beyond 1 and beyond -1, we have divergence. So you might ask the question, to what does this converge? To what does this converge? And you know how to find the sum of an infinite geometric series. The sum of an infinite geometric series is the first term over 1 minus r, right? So this power series converges to this sum on this interval. It would be helpful for us to be able to see that. Let's talk about what we mean by converging. So I'm going to write out some of the terms of the sequence. And this is a partial sum. This is a partial sum. Let's take a look at what we think the sum is. Well, that's interesting. In this area, the blue graph is basically the red graph. But outside of this area, the blue graph is not really the red graph. Well, why not? What did we say is the interval of convergence? -1 to 1. So maybe if I were to change my window, maybe I'll show you that area. Well, looky there. In our window, the blue graph is really close to the red graph. Now, obviously, if I were to add more terms, if I were to add more terms correctly, look, the black graph is closer to the red graph and hangs out longer. We could just keep going. Plus x, oh no, plus x to the 6th, plus x to the 7th, plus x to the 8th, plus x to the 9th. In that -1 to 1 window, the black graph and the red graph, look how close those are. Here, do a trace. This is the black graph at 0.63. This is the red graph at 0.63. Black, red, they're really close at 0.63. So what do we have? What does it mean to converge? To converge, we mean that as we take more and more partial sums, as we take partial sums for larger and larger n values, these polynomials start looking like this function on the interval of convergence. That is the basic idea. So, example 2. For what values of x does the series sum as n goes from 0 to infinity of -1 to the n over 4 to the n times x minus 5 to the n converge? Well, that's just weird, isn't it? That's just weird. And you could write out the terms. You could write out some terms, couldn't you? What is this? If n is 0, that's 1. Oh, that's a problem, isn't it? You got to start at 1. got to start at 1. If n is 1, then this is negative 1 over 4 times x minus 5. And then if n is 2, this is plus 1 over 16 times 2 times x minus 5 squared. And then if n is 3, this is minus 1 over 64 times 3 times x minus 5 cubed, plus, and so on. That's the series. I want to know for what values of x does that converge? Well, this is one of those weird series where I'm trying to figure out, okay, if this series were given to me and it was just this and I had to figure out, does it converge? I don't know about you. I'm using the ratio test. I think I can use the ratio test. The ratio test says, row, row, row your boat gently down the stream. It's the limit as n approaches infinity of the absolute value of the n plus 1 over the nth term. In the n plus 1th term, now we're taking absolute values, so we totally ignore that. This is the only thing in the numerator. The denominator's looking like so. Over the nth term. And then we take a limit at infinity. When we take a limit at infinity, this goes and most of those go. This goes and most of those go. And we take a limit at infinity. When we take the limit at infinity, the n and the n plus 1 behave the same way. So we've got the absolute value of x minus 5 over 4. Remind me what the ratio test said. The ratio test said that this series will converge if this is less than 1. So when does that happen? That happens when negative 1 is less than x minus 5 over 4 is less than 1. And I'm pretty sure if you were to multiply everybody by 4 and add 5 all the way across, you would get negative 1 less than x less than 9. No, that's silly. You'd get positive 1 less than x less than 9. In fact, you would get positive 1 less than x less than 9. What does the ratio test say? The ratio test says in this interval, this series will converge. Absolutely. If we're beyond 9 or beyond 1, rho will be greater than 1, and this series will diverge. What happens at 1? What happens at 9? That's a good question. At x equals 1, what happens? You sub in 1, you sub in 1, you sub in 1. What happens? I have to give you a moment to think about that. Okay, it's just the sum of the 1 over n's. And that diverges. So at x equals 1, no, nothing doing there. But what happens at x equals 9? I've got to give you a moment to think about that. What happens at x equals 9? Sub in 9, sub in 9, sub in 9. What happens? Well, if that happens, you have the alternating harmonic series. And we know from our previous work, the alternating harmonic series converges. So the interval of convergence goes from 1 to 9, not including 1, including 9. That's what the ratio test tells us. Okay, I'm going to go one more. For what x does, whoa, sorry about that. How about that? How about I actually do my job? There we go. Does this converge? And it's the sum as n goes from 0 to infinity of x to the 2n over 2n factorial. Want to know what x make this converge? And again, you could write out some terms. You could sub in 0 and get 1. You could sub in 1 and get x squared over 2 factorial. You could sub in 2 and get x to the 4th over 4 factorial, and so on. This is the series that I want to know, does it converge? It's got factorials in it, so it's a pretty good guess that we'll use the ratio test. Let's use the ratio test. Row, row, row your boat gently down the stream. Its limit is n approaches infinity of the absolute value of the n plus 1 term over the nth term. The real question is, do you know how this all simplifies? And I think that you do. These cancel out with most of those, leaving you with x squared. This cancels out with most of those, leaving you with 2n plus 2 and 2n plus 1. And the question is, as n gets large, what happens to this? Well, there's no n's in the numerator. There's 4n squareds in the denominator. So as n gets large, the denominator gets large, this goes to 0. So the real question is, for what values of x is 0 less than 1? And I think it's obvious the interval of convergence has to run for all values of x, because for any value of x, 0 is less than 1. So recapping, there are 3 possibilities for convergence of an infinite series. By far the most common is that the series will converge on some interval from a minus r to a plus r, and perhaps at the endpoints of the interval. This is by far the most common. Example 2, example 1, these are the most common. This happens when rho is less than 1 for some x, but not all of the x. Option 2 is that the series converges for all x. And this is what happens when rho is less than 1 for all x. And then the third option is that the series will converge at x equals a, but diverge elsewhere. And that's what happens when rho is greater than 1 for all x. Those are the only 3 options. This is the rarest option. This is rare, but it exists. This is the one we're going to play with most of the time. Okay? So for you to play with, I would like you to find the interval of convergence for x to the n over n factorial, negative 1 to the n times x minus 3 to the n over the square root of n squared plus 1, and the sum as n goes from 0 to infinity of n factorial times x to the n. And so we're clear, there's one example of each of the 3 types in this OYO. One of the series has an interval of convergence for all x values. One of them converges only for x's in an interval, not negative infinity to infinity, and one of them only converges at one particular point. So good luck with those, and I will see you when we gather in class.